Well, my dear participant, we are still continuing on time series analysis with R, and we were talking about, I think, random walk. Yes, now we are going to talk about simulation of time series data. Arima.sim is the function. The function arima.sim the function arima.sim works for all forms of subsets of arima models. In our arima.sim, we will accept many arguments, but we are interested primarily in three of them. N is the length of the desired time series, model a list of the following, and they are list of the order, and that is order these orders P, D and Q. Here P stands for the order of the AR model, Q stands for the order of the MA model, and D stands for the differencing. And third argument is SD. The standard deviation of Gaussian error by default it is SD is equal to 1. So if it is not specified, it means it is SD is equal to 1. Simulation from ARP model. Mathematically, ARP model is defined as xt is equal to phi 1, xt minus 1 plus phi 2, xt minus 2, etc. plus Wt. Wt is the white noise. Let us begin by simulating AR1 models and comparing their behavior. First, let us choose the model with constraining AR coefficients. Recall that in order for an AR1 model to be stationary, phi must lie between minus 1 to plus 1. So we will try with 0.9 and 0.1 and 0.9, a very small value of phi and very large value of phi. And we will again set the function number with set.seed. So here ARM underscore SM list order is equal to C. So it is AR1 because P is 1, rest are 0. So it is AR1 model and AR coefficient is 0.1. Then list description of AR1 model with large coefficient. Here AR1 AR is again AR underscore LG list order C100 AR is equal to 0.9. Now we are simulating. So AR1 underscore SM is equal to AR1 SM is equal to arima sim n is equal to 50. Model is equal to AR underscore SM, that is this model, and SD is equal to 0.1. Then second model AR1 LG large, arima sim n is equal to 50 observations, model AR underscore LG, SD is equal to 1. Now let us plot the two simulated series. Per MF row C is equal to 1 comma 2, it is 1 row and 2 columns, and C get y limits for the column plots. Y LM is equal to C min, minimum of y limit, minimum of AR SM1 and comma AR1 LG. and maximum. So, this is the YLM, this is the limit of the, this is the range, this is the limit of the y axis. And then plot dot TS AR1 SM YLM is equal to YLM, YLM is equal to YLM, YLab is equal to expression italic X italic T, and main expression phi is equal to 0.1. Plot dot TS AR1 LG, and here phi is equal to phi paste phi is equal to 0.9. So, these are the graphics, these are the graphics, these are the graphics. See here, with point time series with the smaller value of AR, that is this one, coefficient is more choppy. It is more choppy and seems to stay closer to 0. It seems to stay closer to 0. Whereas the time series with larger AR coefficient appears to wander around more. It wanders around more. It wanders around more. Remember that as coefficient in AR1 model goes to 0, the model approaches a white noise. So, because a smaller value, it looks like white noise. It looks like white noise. As the coefficient goes to 1, however, the model approaches a random walk. This is a kind of random walk. So, when it goes around 1, it behaves like a random walk, which is not a stationary in either the mean or variance. Next, see now first I will run these commands. I will show you how to get these. See, just I will go into view, then panes, and it is right. So, I want to keep in the right upper. So, now these are the simulated values. Then let us have the two simulated plots. See, with phi is equal to 0.1, it looks choppy and it is more close toward the white noise, whereas this one with phi is equal to 0.9, it looks like a random walk. So, this is the main difference between the choice of phi 0.1 or closer to 0 or 0.9. So, this is a big difference. Now, let us generate with AR 0.5 and minus 0.5. See what happens. AR positive with 0.5 and AR negative with 0.5. See what is the effect. Then we are simulating them and see what is the difference. Phi 1 is equal to 0.5, 0.5. See, it is more choppy with phi 1 is equal to 0.5 as compared to this. Now, it appears like both time series vary around mean. They vary around mean by about the same amount, but the model with negative coefficient produces a much more sawtooth time series. It turns out that any AR1 model with minus 1 less than phi less than minus 1 less than phi less than 0, that is negative values, will exhibit the 2-point oscillations you see here. it looks like this, whereas with positive values it looks like this. Now just I would like to run these. First we are simulating and then we are making a plot. And see this plot we have already discussed. Now, what will be the correlation structure of ARP processes? What will be the correlation structure of ARP processes? Set.seed 1, 2, 3. The 4 AR coefficients. The 4 AR coefficients, they are AR underscore P coef 0.7, 0.2, minus 0.1 and minus 0.3. Empty list for storing the models. AR1 underscore models is equal to list. So it is an empty list. Then loop over order of P. See P 1:4. So P is equal to 1, P is equal to 2, P is equal to 3, P is equal to 4. And assume SD is equal to 1. So not satisfied. Now see here ARP, AR underscore mods, and then this is the listed data object. This is the listed data object. So that's why we are putting this subscript here. So arima.sim n is equal to 10,000 list AR is equal to ARP coef 1:P. So it will take the coefficient 0.7, 0.2, minus 0.1 and minus 0.3, and then it will be simulating. Then it will be simulating, and those 4 simulations are being here. Now par MF row 4, 4,3 means it is 4 rows and 3 columns. These are the 4 rows and 3 columns. So it is because of this. Margin is equal to 1, 4, 1. So here margin on this axis it is 1, here it is 4, then 1 and then 1 for each figure. And then see, we are selecting just 50 observations from each simulated data, first 50 observations. So that is why AR mod P, and we are selecting just 50 observations. Ylab paste AR P sep is equal to, there should not be any space between AR1 and AR2 etc. because of sep is equal to this. Then ACF, this is the ACF. This one is for time series plots, and then it goes for ACF plots. These are the ACF plots. Lag is equal to 12, and then partial autocorrelation function PACF plots. So these are the PACF plots, and they are AR1 is with 0.7, AR2 0.1, no AR1 0.7, 0.2, minus 0.1, minus 0.3. So these are the AR1 with 0.7, then 0.2, then minus 0.1 and minus 0.3. So these are the coefficients, and these are the behavior of the ACF plot, and these are the behavior of the PACF plots. See figure 1.9, time series simulated ARP process, left column time series of increasing order 1:4 rows with their associated ACF center. This is the ACF center and PACF in the right column. Note that the first 50 observations of XT are being plotted. It is evident from the figure, from this figure, that the ACF for ARP processes tails off towards 0 slowly. It tails off towards 0 slowly. After these lags it goes to 0. After these lags it goes to 0. So it goes to 0 slowly. Whereas but PACF, partial ACF plots, goes to 0 for lag greater than P. See here it is P is equal to 4. So it goes to 0 after P is equal to 4. Here P is equal to 3. So it goes after 3, 0. Here it is lag is equal to 2. So it goes after 2, it goes to 0. And here AR1, so it goes after 1 to 0. So these are the observations. Now we can have these plots. And then we can plot them. So these are the plots. I have already interpreted these plots. Now I will go on simulation of moving average MAQ models. Moving average of order Q models. You know this model is defined as XT is equal to WT plus theta 1, WT minus 1, theta 2 WT minus 2, theta Q T minus Q. So this is the moving average model of order Q. We can simulate MAQ processes just as we did for ARP processes using arima.sim. Here are 3 different ones with contrasting thetas. So here MA1, here it is 0.2, here MA1 is 0.8, MA1 is minus 0.5. So here it is a smaller value of MA of the coefficient, here larger value of the coefficient, and here it is negative value of the coefficient. Then we will use arima.sim. Model is equal to MA underscore SM, SD is equal to 0.1, MA model MA underscore large, this is with the small values 0.2, MA LG, it is with large value of the coefficient theta, SD is equal to 0.1, then MA negative, it is with negative value of the theta, and their associated plots, plot.ts, again these expressions I have already discussed. So see, this is when theta is equal to 0.2, when theta is equal to 0.9, it looks like this, theta is equal to minus 0.5, it looks like this. In contrast to AR1 processes, MA1 models do not exhibit radically different behavior with changing theta. As theta are being changed, there is no much change in the behavior of the time series. This should not be too surprising given that they are simply linear combination of white noise, because they are linear combination of white noise. They are randomly, they are some of the independent random observations. So now we can have these plots, white noise, So here we have simulated the data and then we are getting associated plots, and these plots are theta is equal to 0.5. These are the plots, and I have already interpreted these plots. Now, correlation structure of MAQ. We have already seen what is the correlation structure of AR1, but what will be the correlation structure of MAQ process? So, now again I would like to go to the correlation structure of MAQ process. Set dot seed for MA coefficient. So, MA underscore Q underscore coef. So, this is the 0.7 correlation. This is the value of theta 1. The value of theta 1 again 0.2. Here it is minus 0.1 and it is minus 0.3. And then MA mods list, and then we are doing simulation and we are getting the results plot.ts MAQ. See here, so these are the time series plots, these are the ACF plots, and these are the PACF plots. See, figure 1.10, time series of the simulated MAQ process, left column, this is the time series of the increasing order from 1:4 with their associated ACF, center column associated ACF plot, and PACF right column, these are the PACF. Note that only first 50 observations are taken from the plot. Note very little quantitative difference in the realization of the 4 MAQ process. It is evident from the above example that ACF for an MAQ process goes to 0 after lags greater than Q. Here lag is 4, so it goes to 0. Lag is 3, so it goes to 0 after 3. Lag is 2, it goes to 0 after. Lag is 1, so it goes to 0. But PACF plot tails off towards 0 very slowly. Here PACF goes to 0 very slowly. This is an important diagnostic tool when trying to identify the order of Q in an ARIMA PQ models. So, this is the way we can identify what should be the value of P, whether value of P should be 1, Q should be 1 or 2 or 3 or 4 on the basis of ACF and PACF plots. So, we can go and we can run these. These are the simulations and these are for the graphics. So, these are the graphics which we have already interpreted, we have already discussed. Now, simulating and fitting ARMA PQ process. Now, we are going to fit ARMA autoregressive moving average model with order P of AR and Q of MA process. And ARMA PQ process is a mixture of ARP and MAQ processes. It can be written as XT is equal to phi 1 xt minus 1. So, up to this it is ARP model, and after this one Wt plus theta 1 up to Wt minus q. So, this is MAQ model. So, this is the mixture of AR as well as MA process. ARMA PQ process can be simulated using arima.sim function, whereas to fit an ARMA model, the function arima x order, where x a univariate time series, order a vector of the length 3 specifying these things. Let us see an example of ARIMA works. First, we simulate ARMA 2, order of AR is 2, order of MA is 2 model, and then estimate the parameters to see how well we can recover them. Set.seed 1, 2, 3, ARMA 2, description of an ARIMA. So, ARMA 2 list order C. Here P is 2 and Q is also 2, but difference is 0. AR, the coefficient here it is minus negative and here it is positive, whereas MA coefficient both are positive. This one is larger and this one is smaller. Mean of the process mu is equal to 5. Simulated process mean C. ARMA sim, arima.sim, n is equal to 10,000, model is equal to this one, and plus mu. So, mu is also being added in this. Estimate parameters, arima x is equal to arima.sim, this is the ARMA._sim. So, this is the model, order is this, and we are getting the results. See the coefficient minus 7, the simulated value is minus 7, and here it is also estimate is minus 7. Then AR2 it is 0.2, it is 0.19. MA1 0.7, it is 0.69, so 7, and MA2 it is 0.2, so it is 0.2, and these are the standard error, and this is the intercept. The intercept mean is 5, mu is equal to 5, so it is giving 4.9975. So, actually it is confirming the simulation. This parameter estimation confirms the simulated data. So, now we can go and we can run these commands and get the result. So, these are the results. These are the results which we had just discussed. Now, in my next lecture, I shall talk about Box-Jenkins methods.